Welcome back to Physics 192. I'm Gerard Blanchard. Last time we talked about induced electromotive force. That is, an electromotive force that can drive a current in a conducting loop when there is a changing magnetic flux through the loop. Last time we looked at that in terms of the magnetic forces on the charged particles in the conductor. This time we're going to look solely at the change in the magnetic flux through the loop, and that leads us to what we call Faraday's law. Faraday's law states that the magnitude of the electromotive force is given by E, the electromotive force, is equal to the absolute value of the change in the magnetic flux through a loop divided by the change in time, or the time over which the change in magnetic flux occurred. So E is equal to the absolute value of the change in phi sub m, that's the change in magnetic flux, divided by change in time. A couple of notes. I always treat electromotive force as a positive quantity, which is why we have the absolute value bars there. And I will include the number of loops in the magnetic flux, whereas your book does not. It will introduce in separately when it needs to, but I'm going to include in the definition of magnetic flux. So we can, going back to our equation, E is equal to the change in magnetic flux over change in time. Remember that magnetic flux is the number of wraps in a loop times the magnetic field through the loop, times the area of the loop, times the sine of the angle between the magnetic field and the area. And there are three things in there that can change: the magnetic field, the area of the loop, or the angle that the face of the loop makes with the magnetic field. So we can have three different expressions for the electromotive force depending on what is changing. So we have electromotive force is equal to the absolute value of N times the change in the magnetic field over the change in time, times the area, times sine and theta, if it's the magnetic field that's changing. Or the electromotive force is equal to the number of wraps of wire in the loop times the magnetic field times the change in the area of the loop over the change in time times sine of theta, if the area of the loop through which the magnetic field passes changes. Or finally, the electromotive force is equal to the number of wraps of wire times the magnetic field times the area of the loop times the change in the sine of theta with respect to time if it's the angle that's changing. So depending on what is changing, we can have three different expressions for the electromotive force, but they always include the terms N, B, A, and sine of theta. That's the magnetic flux. And we have the change in whatever is changing with respect to time. So Faraday's law gives us the magnitude of the electromotive force. What about the direction of the current that is induced in the loop? That is given by Lenz's law. Lenz's law states that the direction of the induced current is such that its magnetic field opposes the change in magnetic flux. Finally, the magnitude of the induced current is given by this equation. The induced current is equal to the electromotive force divided by the resistance, the electrical resistance. That's that letter R. So I is equal to electromotive force divided by R, or resistance. Resistance is measured in units of ohms. We're going to go much more into depth into this later. We're going to go into resistance when we talk about electric circuits. But for now, all you need to know is that it's a property of a conducting loop. It has has a certain resistance measured in ohms, which in the symbol for ohms we'll see as a capital Greek omega. And the greater the resistance, the less current we get in the loop. The greater the electromotive force, the more current we get in the loop. Let's do some examples. Take a look at this diagram where we have an area, that's the dotted box, with magnetic field lines represented by the dots coming out of the page. So we have an area where we have a magnetic field coming out of the page. And then we have 4 loops. Some are moving into the magnetic field area and some are moving out. And as they move out of the area where there's a magnetic field, the magnetic flux through the loop will be decreasing. As they move into the area where there's a magnetic field, the magnetic flux through the loop will be increasing. And as we saw in a previous example, this will induce an electromotive force, and this will induce a current in these loops. We looked at this and we answered the question of the direction of the current previously using the concept of the magnetic force on the electrons in the wire. Now we're going to use Lenz's law to figure out the direction of the current in each of these loops and answer the question, which of these loops feels a force to the right? That's the actual question that's being asked here. Now, Lenz's law says that the induced current will be in such a direction that it opposes the change in magnetic flux through the loop. Take a moment, draw this diagram, and think about the answer to the question, what is the direction of the induced current in each of these loops, and which of these loops feels a force to the right? Okay, let me draw my diagram. Here is the area where there is a magnetic field coming out of the page. There are my magnetic field lines. And let's start with the first loop. This was loop 1, was moving to the left out of the area where there's a magnetic field. So the magnetic field only goes through this part of the loop, and as I'm pulling the loop out, the area decreases because this side is moving further and further and further to the left. So the change in magnetic flux is negative. The magnetic flux is decreasing. So for this case, the magnetic flux is decreasing. The induced current will be such that its own magnetic field will counteract the change in the magnetic flux. Or in other words, since the magnetic flux, which is out of the page, is decreasing, the current will give us a magnetic field that is out of the page to supplement what is being lost, what magnetic flux is being lost to the loop as it gets drawn out of the magnetic field. So what direction of current, either clockwise or counterclockwise, will give us a magnetic field that comes out of the page? The answer is counterclockwise. If I imagine grabbing this bottom wire, I'm going to grab the bottom wire and I'm going to put my thumb to the right to represent a current in the bottom wire to the right, then my fingers will curl out of the page. Same thing if I grab the right wire with my thumb to the top, my fingers, as they curl around the wire, will curl out of the page in the middle. Same thing on the top. So a current that is induced in the counterclockwise direction will give us a magnetic field that is out of the page. And so we'll call this B from the induced current. I'll call it B. I'll call it B1. So this is the magnetic field that exists and it is making a flux through the loop. This is the magnetic field from the current in the loop itself. So as the magnetic flux from this area through the loop decreases, the loop creates a current that adds some more magnetic field in that direction. Let's take a look at the second loop, which is also moving to the left, but it's moving to the left into the magnetic field. Now, as this loop moves to the left and gets more and more in the area where there's a magnetic field, the magnetic flux through this loop is increasing. So the magnetic flux through this loop is increasing as it gets more and more of this magnetic field through its area. Because by Lenz's law, the induced current will oppose that increase in the magnetic field, so that will give us an induced current that will create a current, that will create a magnetic field into the page. So B1, we want a B1 that is into the page. So as this magnetic flux increases through the loop will induce its own current that will create a magnetic field to fight the increasing magnetic flux through the loop. And what direction of current, either counterclockwise or clockwise, will give us a magnetic field that's into the page inside the loop? That would be a clockwise current. Yes, a clockwise current. So if the current is induced in the clockwise direction, then the magnetic field from that current will give us a magnetic field that opposes this increasing magnetic flux through the loop. And this is the same answer as we got from our previous example, but we're looking at it in a different way. Now, really quickly, what is the direction of the magnetic force on each of these loops? Well, on this side, we have a current that is up, a magnetic field that is out of the page. So this side of the loop is going to feel a force to the right. This side of the loop, the top, is going to feel a force that is up. This side of the loop is going to feel a force that is down. We have a current in that direction. A magnetic field out of the page is going to give us a force down. And there's no magnetic field over here, so there's no force. So these two forces are going to cancel each other out, and we're left with a force to the right. So as we try to pull this loop out of the magnetic field, the induced current will try to keep it in the magnetic field. Over here, the current on this side is upwards. The magnetic field is out of the page. So this side of the loop feels a force also to the right. This side on the bottom feels a force that's upwards. And on the top, we get a force that's downwards. So, and over here there's no force because there's no magnetic field to exert a force on this current. So these two forces cancel out and we're left with a force to the right. So as we try to push this loop into the magnetic field, the magnetic force on the induced current actually pushes back. So if the loop is not in the magnetic field, there is resistance to pushing it in. If the loop is already in the magnetic field, there is resistance to pulling it out. Let's take a look at the other two examples. We have number 3, which is going into the magnetic field, and number 4, which is going out of the magnetic field, both to the right. Okay, so as this loop goes into the magnetic field, the magnetic flux is increasing. Magnetic flux is increasing, so B1, the magnetic field of the loop, will oppose that increase by creating its self-magnetic flux that's into the page. What is the direction of a current that gives us a magnetic field into the page? Well, that is going to be a clockwise current. So the induced current in this case is clockwise, and the force on this side is going to be down. I mean, the current is down, the magnetic field is up, so this loop will feel a force back out. So once again, as we try to push this loop into the magnetic field, there's resistance. There is resistance to changing the magnetic flux through a loop. Here, the loop is in the magnetic field and we're trying to pull it out. So the magnetic field is like that. The magnetic flux is upwards, and it is decreasing as we pull the loop out, phi decreasing. And so if phi is decreasing, then we're going to get a magnetic field, B1, the loop's own magnetic field, that is out of the page to supplement the lost magnetic flux. And what direction of current will give us a magnetic field that's out of the page? Well, it will be counterclockwise. And so the current is down right here. We have a current that's down, magnetic field out of the page. There will be a force to the left. So once again, as we try to pull this loop out of the magnetic field and decrease the magnetic flux through it, there is resistance. There is a force that is pulling to keep it in the magnetic field. So this is another way to think about induced currents, so induced electromotive force and currents. So this is another way to think about induced electromotive force and currents, and it only has to do with the changing magnetic flux through the loop as given by Faraday's law. Let's work another example. A 15-gram conducting rod of length 1.3 meters is free to slide downward between two vertical rails without friction. The rails are connected to an 8-ohm resistor, and the entire apparatus is placed in a 0.45 Tesla uniform magnetic field. Ignore the resistance of the rods and rails, so the total resistance is 8 ohms. And the question is, what is the terminal velocity of the rod? Or in other words, what is the speed with which the rod will slide downwards such that the magnetic force on the induced current is equal to the weight of the rod. So that's the real question here. What is the speed with which the rod can slide downwards so that the magnetic force on the induced current is equal to the weight of the rod? Go ahead and draw your diagram, list your knowns and unknowns, and think about this question. Let's draw our diagram. Here are our rails and our slider. And we know that the separation L is equal to 1.3 meters. That's the separation from here to here, because that's the length of the rod. The rod has a weight which is equal to its mass times g, or the mass is 15 grams, so that would be 0.015 kilograms times g of 9.8. So the weight is equal to 0.015 times 9.8. That would be 0.147 newtons of weight pulling the rod down. There is a resistor with a resistance of 8 ohms. That's a capital Greek omega representing the unit of ohms. And there is a magnetic field that is out of the page. I'll draw it in. And the magnetic field strength is 0.45 Tesla. And we know the rod will be moving down with some V that we don't know. But we do know that as it moves down, there will be an induced current because the magnetic flux through the loop here is going to increase as the area of the loop increases. And so there will be a magnetic force equal to the current times the length of the wire, the length of the slider times the magnetic field strength. And we want to know the terminal velocity of the rod, which would be the speed at which the rod is in equilibrium. So we know that we have an equilibrium situation. Let's call this our y direction. We know that we have equilibrium, which says that the total force in the y direction is equal to 0, or Fm, which is up, minus the weight is equal to 0, or Fm is equal to the weight, or I times L times B is equal to the weight. We know the weight of the bar, we know the magnetic field, we know the length of the wire. So this actually tells us what the induced current is when the bar is in equilibrium. So let me solve that for I. I is equal to weight over L times B, or the induced current, is equal to the weight of the bar, 0.147, divided by the length of the bar, which is 1.3 meters, times the magnetic field strength, which is 0.45 Tesla. So the induced current, when the bar is in equilibrium, is equal to 0.147 divided by 1.3 times 0.45. So we're looking for an induced current of 0.251 amperes. So based on the fact that we're in equilibrium, we know, based on the fact that we're looking for the equilibrium situation, we know that we have to get an induced current of 0.251 amperes. Okay. So what can we do with that? Well, we know that the induced current is equal to the electromotive force divided by the resistance. Knowing what the current that we're looking for is and the resistance, that tells us what the electromotive force must be. So I times R is equal to the electromotive force. The current is 0.251 amperes. The resistance is 8 ohms. So the electromotive force that we're looking for is 0.251 times 8, or 2.01 volts, is equal to the electromotive force. So we're looking for an electromotive force of 2.01 volts. Is that going to tell us the speed of the rod? Yes, it is, in fact. Because what is going on here? As this slider slides down, the magnetic flux through the loop increases. The magnetic flux through the loop increases due to the increase in area. So the expression for the electromotive force that we use here would be that the electromotive force is equal to the absolute value of the N times B times the change in the area of the loop over the change in time times the sine of the angle between the magnetic field and the face of the loop. Okay, let's see what we can do with this. We only have a single loop here, so N is equal to 1. B is equal to 0.45 Tesla. We have the change in the area over the change in time. We'll come back to that. And the angle between the magnetic field, which is out of the page, and the face of the loop, which is in the plane of the page, is 90 degrees. So the angle between the magnetic field and the face of the loop is 90 degrees. And the sine of 90 degrees, well, I'll just write sine of 90 degrees. And we know that that is equal to 1. Okay. So what do we have here? We have the electromotive force is equal to 1 times 0.45, so 0.45, times the change in area. Oh, I'll write that again. Change in area over change in time. Now, what is the change in area of this loop right here with respect to time? Well, it's equal to this width, which is constant, times the speed with which this bar moves down. So this bar moving down changes this area. So the electromotive force is the absolute value of 0.45 times the, well, actually I'll expand that just a little bit. The change in area is equal to the change in the height of the loop times the width of the loop. The width of the loop is L, and the change in the height of the loop over time, so I'll write that as L, which is the width of the loop, times the change in the height of the loop over time. So the electromotive force is 0.45 times the width of 1.3, and the change in the height of the loop, the change in the height here over time, is just the speed of the bar. So delta H over delta T is just the speed of the bar. And so finally I have the electromotive force is equal to the absolute value of 0.45 times 1.3 times the speed. Well, actually, I haven't done anything there, have I? We know what the electromotive force is. The electromotive force is 2.01. So 2.01 is equal to 0.45 times 1.3. which is 0.585 times V. And since this is a positive number and the speed is also a positive number, I actually don't need my absolute value bars, since we're dealing with speed, which is a positive number. And I can finally write that 2.01 divided by 0.585 is equal to the speed of the bar. And so that would be 2.01 divided by 0.585. And we get that the speed of the bar must be 3.44 meters per second. So if the bar is moving down at 3.44 meters per second, then the forces on the bar will be in equilibrium. So 3.44 meters per second is the speed. So as the bar moves down at that speed, weight is pulling down, and we must get a magnetic force that is upwards. Let's just check that. As this bar moves downwards, then the magnetic flux through this loop is increasing. So we're going to get a current that gives us a B1 that is into the page. And so that would be a current that is down on this side, to the left on the bottom, up on this side, and in this direction on the top. So the current, I, is going to flow clockwise in this loop. And then on the bar itself, we have a current that is to the right, to the left, a magnetic field that's out of the page. So the force on the bar will be upwards, or in other words, opposing the change in magnetic flux. So yeah, so we do get a force that's upward that will be balanced by the weight that's downward. And when those two are balanced, the bar is in equilibrium and it will move at constant speed. So that is the answer to the question that we were asked. What is the terminal speed, or what is the speed of the bar when it is in equilibrium. Let's work one more example. A square loop of wire, 0.75 meters on each side, has one edge along the positive z-axis and is tilted towards the YZ plane at an angle of 30 degrees with respect to the horizontal, which is the XZ plane. There is a uniform magnetic field of 0.32 Tesla pointing in the positive x-axis direction. If it takes 0.2 seconds to increase the angle to 60 degrees, what is the induced voltage or EMF in the loop? And while the angle is being increased, which direction will current flow through the top side of the loop? You have a diagram there, so go ahead and reproduce that diagram. So what we have here is that the plane of the face of the loop is changing with respect to the magnetic field direction, and so we have a change in angle, which is driving a change in flux, which is driving an induced electromotive force. Okay, let me reproduce that diagram that we were given. X, Y, Z. The magnetic field is in the X direction, and our loop initially makes an angle of 30 degrees with respect. So that would be, I'm going to write that as theta initial. Theta initial is 30 degrees. And finally, it makes a steeper angle. And I'll write that as theta final is equal to 60 degrees. So theta initial is 30 degrees. Theta final is 60 degrees. The change in time, T final minus T initial, is 0.2 seconds. The magnetic field strength is 0.32 Tesla. And the height and the width of the wire is 0.75 meters, or in other words, the area of the wire is equal to 0.75 meters squared, which is 0.75 squared is 0.562 square meters. So I think we have everything. We've got the area of the wire, we've got the initial angle, we've got the final angle, we've got the magnetic field, we've got the change in time. Alrighty. And what we're looking for is, what is the electromotive force? That is what we're looking for. Well, the electromotive force is equal to the absolute value of the change in the magnetic flux over the change in time. What is changing here is not N, not B, not A, but the sine of theta is changing. So you have a change in sine of theta over a change in time. So that is the form of the change in magnetic flux that we're going to use here. electromotive force is equal to N, which is 1, B, which is 0.32, the area of the loop, which is 0.562, times the change in the sine of theta. The change in the sine of theta would be sine of theta final minus sine of theta initial. That is the change in the sine of theta over the change in time. That's t final minus t initial. That's 0.2 seconds. And my absolute values. And so what do we have here? We have E is equal to the absolute value of 1 times 0.32 times 0.562 times sine of theta final, which is 60 degrees, minus sine of theta initial, which is 30 degrees, all divided by 0.2, absolute value. And what do we have? We have 1 times 0.32 times, start that again, 1 times 0.32 times 0.562 times, and now parentheses, sine of 60 degrees minus sine of 30 degrees, and all divided by 0.2, and I get 0.329. And so I have the absolute value of a positive number. I can drop those absolute value bars. So the electromotive force is 0.329 volts. And that is part of what we were looking for. What is the induced voltage? 0.329 volts. And the second question was, what is the direction of the induced current? Well, okay, let's think about this. As the loop tilts upwards, then actually, let's look at it from the side on. Here is the magnetic field going to the right, and the loop is tilting upwards. As the loop tilts upwards, the magnetic flux increases. And in fact, we saw that because the sine of 60 was greater than the sine of 30. Or in other words, there's more magnetic flux through the loop as the loop tilts upwards. So the magnetic flux is increasing through the loop, so the current in the loop will create a magnetic field in itself that opposes the increase in magnetic flux. So phi is increasing, so B1 is going to be opposite the magnetic field. So a magnetic field is like this. Our induced magnetic field is in the opposite direction. So we want a current that will give us a magnetic field to the left through that loop. And I'm going to grab imagine that I'm grabbing the top of this loop, okay? I'm grabbing this wire right here. I'm going to grab the top of the loop, put my thumb in the direction, in the negative z direction there, put my fingers through the loop, and my fingers are pointing to the left, just like we want them. So the magnetic field, the current, the induced current, I, must be flowing in this direction, and then it will continue around the loop. So the induced current I is flowing in the negative z direction. It's flowing towards the back to give us a magnetic field that opposes the change in magnetic flux. So that's Faraday's law and Lenz's law. Faraday's law says that whenever the magnetic flux through a loop changes, there is an induced electromotive force in the loop. Lenz's law says that the current driven by the electromotive force is in the direction that opposes the change in magnetic flux. These are two important ideas for understanding a lot of electromagnetic phenomena, and we're going to come back to them throughout the course. We're going to work some more examples next time. Until then, think physics.